For many of you, this may be the only numerical modeling class that you take. So I want to make sure that you know what we will and what we won't cover as part of this class. In effect, I don't expect you to be an auto mechanic by the end of this class. I don't think you'll be able to diagnose and build models. It's not really the objective. At the same time, I don't want you to look at models as self-driving cars. I want you to understand that as a user, you have a lot of input to make a model work properly. I'm aiming for a happy medium. So let's jump right in. We'll consider a 25-cell model. This might represent a domain that's 5 cells on a side. It's homogeneous, and each cell has a k value and a head value. To start with, we're going to focus here on cell 13 right in the middle. Now that number doesn't really matter. It could be any numbering system, but this is a fairly simple one to start with. As is usually the case with subsurface hydrology, it goes back to Darcy. So we're going to use this form of Darcy's equation and put it in a mass balance context. There's flow from cell 12 to 13. It might be positive or negative depending upon the direction. And we can write Darcy's equation with subscripts that refer to the head in 12 and 13 and the effective k between cells 12 and 13. We can do the same for the flow between 8 and 13 and between 14 and 13 and 18 and 13. This gives us 4 equations describing the flow between cell 13 and those cells surrounding cell 13. Because flow is steady state in this model, we can say that the sum of all of the flows into cell 13 must be 0. There's no change in storage with time. Then we can gather all of those terms and reformulate them so that they're all a multiplier of k values multiplied by h values. Now this part is a bit of a stretch. We have 25 cells and we're going to have an equation for each one of those cells. And we also have an h value in every one of those cells. So we end up putting these together in a 25 by 25 matrix. This row, for instance, represents the 13th cell, the one we've been talking about. It is the equation for that cell. But only some of the head values are involved, those in the surrounding cells and the middle cell. If we were to write an equation that had every head cell included, most of those would be multiplied by 0. Every other head cell is multiplied by some effective k, which is a combination of k values that we know. To keep things clean as we move forward, I'm just going to show white cells as those that contain zeros and black cells that contain some combination of k values. We can repeat this for cell 12, of course, just changing the subscripts. We'll end up with another set of black and white cells. We can do this for all of these internal cells, all of the ones that have 4 surrounding cells, and start to fill in the pattern. And then we can look at edge cells, which have flow from 3 surrounding cells and a boundary. If we go through all of this, we'll find that the equation now has something other than 0 on the right-hand side, and it only involves 4 head values, the cell itself and 3 surrounding head values. We continue filling in the pattern, now filling in for cell 4 as shown. And we can also consider the edge cells, which only have 2 surrounding cells and flow potentially from 2 different boundaries. We can extend this for all of the top and bottom cells, and also the left and right boundary cells, thereby completing the black and white check pattern. This we'll then refer to as the K matrix as we move forward, remembering that all of the white cells have value 0 and all of the black cells are combinations of known K values. This is where the math really kicks in. We're going to take this matrix of K values and multiply it by a vector of head values, the head value in every cell, and each of those is going to represent an equation that tells us what's happening on the right-hand side. And remember, the right-hand side was either 0 or it was some function of the boundary flux. In matrix form, then, we have 25 equations with 25 unknowns, each of the head values. That is essentially the mathematical representation of our model. Now, we can do many things with this representation. For instance, what if cell H4 was a type 1 constant head boundary with a value of 7? In this case, we'd replace the head with 7, and we'd have one fewer head to solve for. But we'd still need to know that H4 value because it's multiplied by non-zero K cells in all of the cells surrounding H4. Practically, we replace the H4 value with 7, and the right-hand side is no longer included in any of the equations, so it could default to 0. In more advanced classes, you'll learn why these banded, sparse matrices like this K matrix are relatively easy to solve compared to more complete matrices. For completeness, we'll at least address what we do for transient conditions. Here, the difference is that the change in storage within a cell is no longer 0. It's some non-zero value ds, and we have to account for that as the sum of all the flows equals this change in storage with time. We relate that change in storage to a change in head multiplied by some storage capacity of the porous medium multiplied by the time step. This makes transient problems more difficult to solve because the right-hand side of the equation depends on the head value, but we need to know the right-hand side of the equation before we can solve for the head value. We're almost done. The last thing is to push this into what we call inverse modeling. In this case, we might know all of the head values. Maybe we have measurements in monitoring wells, but we're interested in inferring the K values. So what is the value of K in each cell that gives us the head values that we observe for a steady state model? And of course, for a transient model, it also has to satisfy the changes in storage with time that we observe. Okay, that was a pretty long one, pretty deep. So I hope that you can just let that sink in, maybe take a deep breath, find your happy place, and at least know that you've seen the basics of what happens underneath the hood when we run numerical models.